Light is both wave and particle. The opposite is also true. It is neither. Hold both thoughts. Let them sit uncomfortably together. This is not confusion. This is how reality actually works. For most of my life, I stood at the center of a storm, not a storm of wind or water, but of ideas that threatened to tear apart everything we thought we knew about existence itself. In Copenhagen, in those rooms where young physicists gathered with equations and arguments and coffee that went cold while we debated through the night, we discovered something extraordinary. We discovered that reality has limits, not limits of distance or speed, but limits on what can be meaningfully known at all. The universe, it turns out, refuses to be fully described. Not because our instruments are too crude, not because our mathematics needs refinement, but because reality itself is structured in such a way that complete knowledge is impossible. Some questions that sound perfectly reasonable, questions that feel like they should have answers, are actually meaningless. Nature will not permit them to be asked. Let me take you to where this realization first crystallized. Copenhagen, 1927. The Institute for Theoretical Physics, which I had the privilege to found, had become a place where the brightest minds came to wrestle with the strange behavior of atoms and light. We were discovering that when you look closely enough at the fabric of existence, classical thinking simply fails. The world is not made of tiny billiard balls following predictable paths. It is something far stranger, far more beautiful, and far more resistant to our desire for complete understanding. Consider light. For centuries, we argued, is it a wave or a particle? Newton said particle. Young and Fresnel demonstrated wave behavior through interference patterns. Einstein showed the photoelectric effect requires particles. Photons. So which is it? Both? Neither. The question itself may be imprecise. What we discovered, what the mathematics forced us to accept, is that light exhibits wave behavior in certain experimental contexts and particle behavior in others. Not sometimes one and sometimes the other, depending on its mood, but fundamentally both, in a way that transcends classical categories. The behavior you observe depends entirely on how you choose to look. And here is where the limit appears. You cannot design an experiment that captures both the wave nature and the particle nature simultaneously. If you set up your apparatus to detect interference patterns, wave behavior, you necessarily destroy the ability to track individual particles. If you set up detectors to catch individual photons, particle behavior, you necessarily destroy the interference pattern. Nature offers you one truth or the other, never both at once. This is complementarity. I called this complementarity because these descriptions are complementary, both necessary for complete understanding, yet mutually exclusive in any single observation, like position and momentum, like time and energy, like the wave function before measurement and the definite outcome after. Reality presents itself in pairs of truths that cannot be simultaneously grasped. Einstein resisted this. It pained me to oppose my hero, but he felt certain that beneath the quantum formalism must lie a complete deterministic reality, that our equations were merely approximations of something more fundamental. God does not play dice, he told me. I replied gently that we should not tell God how to run the universe. But the disagreement ran deeper than dice or determinism. Einstein believed that limits on knowledge were temporary, gaps in understanding that future theories would fill. I came to believe that the limits are permanent, woven into the fabric of reality itself. Not limitations of our instruments or intelligence, but epistemological boundaries that define what knowing can mean. Consider what happens when you observe an electron. Before measurement, quantum mechanics describes it with a wave function. a mathematical object representing probabilities, not definite positions. The electron, in some sense, exists in multiple possible states simultaneously. Superposition, we call this. Not that we don't know where it is, that it genuinely doesn't have a definite position until measured. Then you perform a measurement. You interact with the electron using your apparatus. And suddenly, collapse. The wave function transforms from multiple possibilities into a single actuality. The electron appears in one definite location, but here is the crucial point. The measurement itself created that definiteness. Before your interaction, asking, "Where was the electron really?" is meaningless. The question assumes a classical reality that does not exist at quantum scales. This is not a limitation of measurement technique. This is reality refusing to provide the kind of answer the question assumes exists. The electron does not have a hidden position that you simply revealed. The act of observation participated in bringing that position into being. The observer and the observed are entangled, inseparable, mutually defining. In those long evenings at the Institute, walking through Copenhagen streets after hours of debate, I would think about language itself. We use words like position and momentum and particle, words developed to describe everyday objects, not quantum phenomena. When we try to apply these words at atomic scales, they begin to fail. Not because our vocabulary is insufficient, but because the concepts themselves break down. The boundary between what can be meaningfully said and what cannot becomes visible. Heisenberg discovered his uncertainty principle during this period. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This is not experimental imprecision. It is not that measuring position somehow disturbs momentum, like bumping into something in the dark. The relationship is more fundamental. These properties do not have simultaneous exact values to be measured. Reality itself does not provide them. This is the limit Bohr speaks of. Not a limit on speed, like the speed of light that Einstein showed cannot be exceeded. Not a limit on energy or temperature or density, but a limit on knowledge itself. A limit on what questions physics is allowed to ask. A limit that says certain combinations of properties simply do not exist together, even in principle, even with perfect instruments, even with complete understanding of the laws of nature. Nature forces us to use incompatible frameworks depending on what we observe. In one experimental context, we must speak of waves and interference and probability amplitudes. In another context, with different apparatus, we must speak of particles and definite positions and measurements that collapse the wave function. Both frameworks are necessary. Neither is complete. Reality requires multiple, mutually exclusive descriptions. Perhaps this seems frustrating. We want the complete picture. We want to know what the electron is doing when we're not looking. We want reality to be fully describable in one consistent framework that captures everything simultaneously. But reality, it seems, does not care what we want. The universe is structured such that this kind of complete description is impossible, not practically, but in principle. I opposed hidden variable theories, attempts to restore classical completeness by imagining deeper layers of reality beneath quantum mechanics, variables we simply hadn't discovered yet that would bring back determinism and eliminate randomness. Not because I disliked determinism aesthetically, but because the mathematics and experiments suggested that such hidden variables would require faster-than-light influences, or would be forever unobservable, or would lead to contradictions with quantum predictions that proved remarkably accurate. Trying to go beyond quantum limits, I came to believe, is like asking what color a sound is. The question itself breaks down. It assumes categories that don't apply. Nature has drawn a line and said, beyond this, your questions become meaningless. This does not mean we know nothing. It means that what we can know is limited by complementarity, by the necessity of choosing which aspects of reality to observe, knowing that choice excludes other aspects. By the measurement problem, the fact that observation participates in creating observed reality rather than passively revealing pre-existing properties. By the structure of quantum mechanics itself, which describes nature in terms of probabilities and wave functions rather than definite, simultaneous values for all properties. Walking through Danish streets in twilight, watching shadows merge and separate, I would think about how observation creates boundaries. A shadow is not an object with independent existence. It is a relationship between light source, object, and surface. In quantum mechanics, the whole universe becomes relational. Properties exist in relationships, not as intrinsic features of isolated systems. The observer, the apparatus, the observed phenomenon, they form a unified, indivisible whole. You cannot speak meaningfully of the electron's properties independent of how you observe it. The limit, then, is conceptual completeness. We will never have a single unified picture that captures all aspects of quantum reality simultaneously from a God's eye view. Instead, we have complementary descriptions, each valid in its domain, each excluding the others, each necessary but insufficient. Together, they form something like a complete understanding, but it is a completion that refuses synthesis into a single framework. Reality, I suspect, is richer than our categories. Existence overflows the boxes we build to contain it. Quantum mechanics succeeded precisely because it abandoned the quest for classical completeness and embraced complementarity instead. We stopped trying to force nature into frameworks inherited from everyday experience and let nature show us how it actually works, even when that violated our intuitions, even when it meant accepting permanent limits on knowledge. The young physicists who came to Copenhagen often arrived expecting to solve these puzzles, to find the deeper deterministic reality beneath quantum randomness, to eliminate the measurement problem and restore classical clarity. Many left changed, having glimpsed how reality might be structured in ways that resist complete description. Some never accepted it. Einstein, to his dying day, sought a more complete theory. I loved him for his stubbornness, even as I believed he was wrong. What does it mean that reality has built-in limits on knowledge? Perhaps it means that existence is participatory, that the universe requires observation to actualize potentialities, that consciousness and matter are entangled more deeply than classical physics imagined. Perhaps it means that the quest for final, complete theories is misguided, that nature will always retain mystery not as temporary ignorance but as fundamental feature. Or perhaps, and this is the possibility I find most beautiful, it means that reality is not a thing to be known, but a relationship to be participated in. We are not external observers cataloging an independent universe. We are participants in an ongoing dialogue between observer and observed, each measurement a question posed to nature, each answer opening new questions that resist the old frameworks. The opposite of a profound truth is also a profound truth. Light is wave and particle. Electrons have position or momentum, never both precisely. Quantum systems exist in superposition until observed, then collapse into single outcomes. The observer cannot be separated from the observed. Reality provides multiple, necessary but incompatible descriptions. Knowledge has limits that are permanent, fundamental, woven into existence itself. And yet, perhaps these limits are not failures but features. Perhaps a universe that refused limits would be less rich, less strange, less beautiful than ours. Perhaps complementarity is not compromise but a deeper form of truth, one that acknowledges how reality exceeds our capacity to capture it in a single frame. In the end, after decades of wrestling with these questions at the Institute, watching new generations arrive to learn quantum mechanics and struggle with its implications, I have become comfortable with uncertainty. Not the uncertainty of ignorance, but the uncertainty of wisdom, the recognition that some questions do not have answers, that reality is structured to resist complete description, that this resistance is itself meaningful. Do I wish I could see the full picture, the complete unified framework that captures all aspects of existence simultaneously? Sometimes. But mostly I have learned to appreciate the view from complementarity, the way different perspectives, though mutually exclusive, together form something richer than any single description could achieve. The limit is real. It is permanent. It is not failure. It is how reality actually works. What lies beyond the limit? That question itself may be meaningless. Beyond implies a there that may not exist. The limit is not a wall hiding something. It is the edge where questions stop making sense, where language fails, where reality gently but firmly refuses to cooperate with our demand for completeness. I do not know, but I am comfortable not knowing. The universe has shown me that this comfort with uncertainty is itself a kind of knowledge, perhaps the deepest kind available to us. We are both spectators and actors in a cosmos that requires participation, not just observation. The limits on what we can know are the terms of that participation. Both. Neither. The question itself transforms when you try to answer it. And that transformation, that refusal of reality to stay within our categories, that is where the beauty lies.